Are you able to see the slides?
Yes, ma'am.
Yes,
Okay.
ma'am.
So in the last class, what we had covered? Anyone? What we did in the last class?
Ma'am, we were talking about importance of angle and orthogonality between angles.
Actually, right. So using the orthogonal, when we computed the orthogonal vectors, we know two vectors are orthogonal if their dot product is 0, and we computed the cosine angle between them. And this cosine angle is known as cosine similarity in the information retrieval domain. So when you will study any other, you can say you will come across the information retrieval, that we say information retrieval in the web when we do, like Google search engine, right? So there we compute the cosine similarity, as we had done one example also for that. We computed the term document matrix, and then on the basis of that considering that term document matrix, we computed the cosine similarity using a particular query. And then on the basis of that, we were trying to find out which is the document which is most similar to the user query, and then we will show that particular document to the user. So that was the real time application that we do when we are working in the machine learning domain. So moving ahead, let's begin with the vector part, continue with the vectors. So now we'll see what is the linear combination of the vectors and what is known as the span of the vectors. See, when we have two vectors, let us say v and w, so the linear combination of the v and w is in the form of av plus bw. So that means the linear combination of these two vectors is the scalar multiple of vector 1 plus scalar multiple of vector 2. And therefore, in this particular combination, a and b are the scalars, and v and w are the vectors. So now, if we have to compute the linear combination of the vector 1 1 1 with the 3 elements, and another element is, let us say, vector v is 1 1 1 and vector w is 1 2 3. Then the linear combination of these two vectors is 6 8 12. So how do we come to know that this is the linear combination of these two vectors? So what do? We just try to find out, you can say, the two scalars. Well, by multiplying these two vectors, we are able to get a new vector. So this new vector is a new scalar, a linear combination of the two existing vectors, which is computed by multiplying each vector with a scalar value. So here we can see when we have multiplied vector 1 with 4 and vector second with the 2, and when we add them, we get a new vector, and this new vector is known as the linear combination of the two existing vectors. So let's say another example. So we can say if one vector is equal to the sum of scalar multiples of other vectors, then it is said to be the linear combination of other vectors. So let's say a is equal to 2b plus 3c. So how do we do that? So AB, so we have to compute A, the new vector, which is the linear combination of the two existing one. So what do? We multiply vector B with 2, and we multiply vector C with the scalar value 3. And when we, after multiplication, we add them, and final vector that we get is the A, that is equal to 11 by 16. So this is the linear combination of the two existing vectors. So that means from here we can say, so you can say we can also consider another definition, whether two vectors are independent of each other or whether two vectors are dependent upon each other. So if one vector is, you can say, can be computed through the linear combination of any of the existing vectors or through the scalar multiple of some other vector, then it is a, we can say, it is a dependent vector. So, or if we cannot compute a vector through the scalar multiples of the existing vectors, then we can say that these vectors are independent of each other. So if we say that vector A and vector B, they are independent of each other or dependent upon each other. So we cannot compute vector A through any of the direct multiples of vector B, so they are independent of each other. And if we can compute through the scalar multiples of any of these vectors, let us say if we have a new vector that is you can say 2 and 4, so in that case it is a multiple of existing vector B. So we can say that the new vector that we are talking about, that is dependent upon the existing vector uh, B, so they are not independent of each other. And if we want to write that in a general form, a linear combination of n vectors up to n. So here we have a1 v1 plus a2 v2. So a1, a2, an are the scalars, and v1, v2, vn are the vectors. And moreover, see, when we are talking about the linear combinations, so your scalars, it's not necessary that your scalars are the positive values only. Their scalars can be zero also, they can be negative also. So can you, now you take out your notebooks and do this. So express vector 9 and 6 as a linear combination of the existing vectors 1, 2 and 1 minus 4 and tell me the solution. What are the scalar values that you are able to get? I hope all are carrying the notebooks with them. Yes? All have the notebooks?
Yes,
Yes,
ma'am.
ma'am.
Okay.
Ma'am, 7 and 2.
Anyone else?
7 and 2.
Okay, so let's see the solution. So what do? We express that as, let us say a1 or a, b or x, y, whatever you can write, x1 into 1, x1, you can say x1 and x2 are the scalar values, which when multiplied with these vectors, they give us the result as 9 by 6. So we can represent these vectors in the form of linear equations that we, so and then we solve the system of linear equations, and then we find out the values of x1 and x2, that is 7 and 2, that you have given the answer, that is correct. Anyone who is not able to understand this can ask right now. Anyone who is not clear about this? Okay, because you have already studied all these things. So if even if you face any problem during the lecture, if you are not able to understand anything, you can ask. Then we compute the span of vectors. See, when we are talking about the linear combination, so it is a related term that we come across, that is span of the vector. So span of vector is a collection of vectors, is you can say it is a set of all possible linear combinations. So whatever linear combinations are possible for any two vectors, we call them as the span of two vectors, or you can say the range of possible scalars which are there, which are used to compute the combination of the vectors. So we can say like s and t are the scalars, and when we multiplied them for any values of s and any values of t, the new vector we can compute any number of the new vectors, that is the linear possible combination of the vectors. So similarly, can you find out the span of the vectors 1, 0, 0 and 0, 1, 1? What will be the span of two vectors which are given? Yes, you just multiply these two vectors as shown above. Like we have two existing vectors 1, 5, 3 and another vector is 2, 1, 7, and we multiply them and get the linear combination. So computing the linear combination, it gives us the complete range or span of all the vectors. Anyone?
Ma'am, STT.
STT. Yes. Right? So this is the span of this particular vector, and s and t may be any real numbers. So hence the span of the vectors is the set of all vectors in R3 whose second and third entries are same. T and T. See, we have to remember S is different. So if we are able to compute one value of T, it will remain same for the other T also, and S can have any of the values. Clear? So this is called as the span of these two vectors. And there are certain things that we have to remember. If we take the span of two vectors in R2, the result is usually in the form of an entire plane. So that means complete range we are talking about for a particular vector, that we, when we plot that in the form of a line, and we when we, it is you can say we are talking about two dimensions. We have R2 means two dimensions, R3 means three dimensions. So when we take the span of two vectors in three dimensions, the result is usually a plane through the origin in the three-dimensional space. And similarly, if we talk about any value greater than 3, the result is plane through the origin in n-dimensional space. We know a bit difficult when we talk about n dimensions. So understanding 2D dimensions and plotting them, or you can say the 3D dimensions, they are quite easy and we can plot and we can visualize, but more than that dimensions, they are a bit difficult to visualize. But we have to understand like that they are in the plane through the n-dimensional space. So when we write that your vector as a linear combination in the form of a theorem, we say let B denote a matrix whose columns are the vectors. So we have seen when we were solving the finding out the linear equations, the values of the scalars. So we had represented them in the form of the linear equations, and those linear equations, you can say, when we express that, these linear equations are further expressed in the form of a matrix. So we express B is equal to x1 b1 x2 b2 and x1 x2 x3. What are these? These are the scalar values, you can say, and v1 v2 v3, they are the vector values. So it is a linear combination of the given vectors, then equivalent to solving a linear system of equations where bx is equal to v. So you can see that as we started with the vectors, and then we are moving from vectors to the matrices, as we have you can say we can represent these vectors in the form of linear equations, and linear equations are further, they are represented using the matrices. So what is a linear equation? It is a polynomial equation in which the unknown variables have a degree of 1. If the degree is more than 1, then it is not a linear equation. It may be a quadratic equation, or you can say it is a polynomial equation where we have the degree of the unknown variables greater than 1. So geometrically, when we represent the linear equation with two variables, it is represented, we know ax plus by is equal to c is the equation of a line. So we can represent these variables using a hyperplane, and the system of linear equations with two or more linear equations with the same variables, we can say. So we can plot them in the hyperplane, and we can say they are the straight line equations. And now when we have to compare or find out the values, we have to say, when we have multiple linear equations, how do we solve them? So if we have two lines of interest, they have a common point, then there is a unique solution. See, all these things I'm just revising because you have already done these things in the 12th class, or maybe in some other math subjects also. And if there is no common point, then there is no solutions. We can say parallel lines have no solution. They only we have a common solution or a unique solution when they intersect at one point. And if the graph of two lines coincides, that means we have infinite number of solutions, because both the lines are intersecting each other at multiple points because they are coinciding. So now when we define that linear equations using the n variables, so it is of the form a1x1 plus a2x2 is up to an xn is equal to b, where x1, x2 are the variables, unknown variables, a1, a2 are the coefficients of these variables, and geometrically we denote them as a hyperplane. And then when we have multiple linear equations, we call them as a system of linear equations. So what is a system of linear equations? It is basically a limited collection of linear equations with some variables, and each of these equation is a hyperplane, and if they have a common point, then there will be a solution, as we have discussed in the previous slide, that if they have these lines, they intersect These lines are nothing but the linear equations. So if the two linear equations, they intersect with each other at some point, one common point, then they have a unique solution. Otherwise they may have, you can say, the infinite solutions, or there may be no solutions. So how do we represent that? Ax is equal to b, as we have seen in the previous slide. These things we have discussed, that any system of linear equations has one of the following exclusive conclusions. Either they will have no solution, or they will have a unique solution, or they will have infinitely many solutions. So these are exclusive to each other. They cannot be two, you can say, two decisions for the two equations. So, and we can say that a linear system is said to be consistent if it has at least one solution, and it is said to be inconsistent, that means it has no solution. So you can say the linear equations are inconsistent in case A, and they are consistent in case of B when we have at least one solution. So here you can see we have different representations of the system of linear equations when we represent that in the form of a matrix. So the first matrix, here we see that A1, A2, A1, A1, 1, 1, A1, 2. So here we know we represent a matrix in the form of rows and columns. And when we have to represent these linear equations, a system of linear equations in the form of a augmented matrix, then we say we are in one, on the left hand side we are writing the coefficients, and on the right hand side we are writing the values to which they equate, that is b1, b2 up to bm. And this matrix of a1, a2 up to an, this is the coefficient matrix of this linear equation. As we can see that these are the linear equations, a1 1 x1, a1 2 x2, like that. And we can represent you can say, so when we have to represent all the values, see this example, x1 plus x2 minus 2x3 is equal to 1. So that means the coefficients of x1 and x2, they are 1, and the coefficient of x3 is minus 2. So we are taking the signs along with that. So because here in the generic form, we are using the addition sign. So that means the subtraction sign is associated with the number that we are using, that is the coefficient. Similarly, 2x1 minus 3x2 plus x3, it gives 2 minus 3, 1, and 3x1 plus x2 plus 4x3 is equal to 7, that gives 3, 1, 4. So here you can see we are taking the, when we have the subtractions signs, we are taking these along with the coefficient values in the matrix. So what is matrix algebra? We say it reduces, basically it helps in reducing the system of equations to the simple equation expressions, and we can adapt to some systematic methods for solving the certain problems. And we know that when we are working with the machine learning, we are let's say, I'll say, when we work with the machine learning algorithms, the most of the data, that is all the data is represented in the form of matrices only. And matrices have rows and columns. Rows are the tuples, columns are the attributes or dimensions that we have in any of the data sets. And when we are working with the kernels, we are working with the, we are not only working with the two-dimensional vectors, we are working with three-dimensional vectors, four-dimensional vectors. Let us consider the example of the images. See, when we talk about images, we first we take the dimensions in the form of, we say 20, let us say the image size is 28 by 28. Then how we represent that in the form of a vector is, we just multiply, we take all the values in a single vector of 28 by 28 matrix into a 1D vector, and then see it is 1D vector when we are talking about, it is a black and white image. But when we have the you can say this colored image, then we have to take the data of the 3 channels, that is RGB also. So in that case, one more dimension is added to it. So we see the multi-dimensional vectors we work when we are working with the images, etc. And or you can say we can have further high dimensions. So in that case, you have to imagine all the data in the form of the matrices which are in the different dimensions. So one, you can say we have matrices of the matrices, like that, something like that we have when we work with in the machine learning. So in the machine learning, you see, so we have seen the simple example of the you have that neural networks. In the neural networks also you have seen. Then we take the example of principal component analysis. There also we are working with the matrices only when we have to reduce the number of dimensions. So there we are this principal component analysis, where we are trying to find out the principal components. Principal components are nothing but the important features. Important features are nothing but the important columns which are contributing much towards the, you can say, getting the good results. So you can say the matrix of size m by n is called the m by n matrix, and a matrix is a set of group of numbers arranged in a square rectangular array enclosed in two brackets. As we represent, all of you know this thing. So we have different types of matrices. We see, we have a zero matrix in which all the elements are zero. Then we have identity matrix, in which can be of any size n, and it is defined as, so if it is a 2 by 2 identity matrix, that means all its diagonal matrix are equal, diagonal elements are equal to 1. If we come across any matrix in which, except the diagonal matrix, all elements are zero and the diagonal elements are equal to unit, that is 1, then it is called as the identity matrix. And in the other case, this unit matrix becomes a diagonal matrix if all the elements are zero except that the main diagonal line, and it can be anything. So your identity matrix becomes a diagonal matrix when the diagonal elements in that matrix, they are not equal. So all the elements in the diagonal matrix are not equal to 1, then we call it as diagonal matrix rather than the identity matrix. Then we talk about the triangular matrices. So here you can say, so if the you have a square matrix, that means if the number of rows is equal to number of columns, then we call it as a square matrix. And it is upper triangular matrix if I is greater than 0, if ai is equal to 0 for I greater than j. And it is called as the lower triangular matrix when, so here you can say the first one is lower triangular matrix where the upper values are 0, 0, 0, and then I is less than j. And in the second case, we can see the upper triangular matrix, we call it, so where the lower values in the diagonal matrix, they are the 0 value. So for ai is equal to 0 for all I greater than equal to 0. So in this case, we can see these two examples. The first is the lower triangular matrix where we have all the elements except the values where I is less than j, and second one is the upper triangular matrix. And similarly, we can talk about the scalar matrix or diagonal matrix whose main diagonal elements are equal to some scalar. Here we can say this unity matrix, we were talking about the identity matrix. See, when the values, the diagonal elements, they are any values except the 1, except means that inclusive of 1, but all the values are not equal to 1. We call any diagonal matrix is equal to identity matrix when all the diagonal elements are equal to 1. And diagonal matrix is, we can say it is equal to, so you can say these are the conditional, some special cases we can say. So this is also a special case of identity matrix where the diagonal elements are not equal to 1, but they are some same scalar value. So here you can say the scalar value is equal to 6. So for all the diagonal elements, so we are calling it as a scalar matrix. When 6 will be represented by 1, we will call it as identity matrix. And if the diagonal elements, that is all the diagonal elements may be any number, you can say any natural number, then we say it is a So then we move on to the transpose of a matrix. So we talk about the various kinds of operations that can be performed in a matrix. Here we see transpose of a matrix. A is denoted by A, superscript we write T, or we can this quotation marks. Then we say that the rows and columns are transpose to each other. Here we can see that when we have a matrix A whose which is of, you can say it is a square matrix, but it can be of any size. It is not necessarily to be a square matrix. But when we are seeing the values, the initial value, let's say this is a A matrix. So when we take the transpose of this matrix, we are converting the rows to the columns. So here you can say this row, the first column is converted to the row. So the in the first matrix, 5, 4, 7 is one column. In the second matrix, it becomes the row. Similarly, 4, 0, 10, it becomes the second row in the new matrix, and 3, 4, 3, it becomes the new row in the second matrix. Right. So that means the transpose of matrix first matrix is equal to this new matrix that we have seen. So transpose converts the row vectors to the column vectors and the column vectors to the row vectors. So the transpose, we can say, if we have a transpose of a matrix and we again take the transpose of that, that will become the original matrix. So here you can see we have one vector matrix which is of size 4 by 2. So when we take the transpose of this particular matrix, it becomes 2 by 4. So the number of rows becomes the number of columns, and the number of columns becomes the number of rows when we take the transpose. Then we move on to the matrix addition. So you already know, when we go for the vector addition, we multiply the corresponding elements in the vectors, and when we go for the matrix addition, we also again go for the corresponding addition of the corresponding elements. So here we are taking 0 plus 1 is 1, 4 plus 2 is 6, 2 plus 3 is equal to 5, 3 plus 4 is equal to 4, 1 plus 5. So I have been moving row wise. So you can say similarly, when we go for the subtraction, we are subtracting the corresponding elements of these two matrices. So what will be the subtraction result for these two matrices? Anyone? What will be the subtraction result for these two matrices that whose addition is given? Anyone tell me what will be the answer?
-1
हाँ
2 हम सब्ट्रैक्ट कर देंगे हर उसको
हाँ हाँ ठीक है, -1 2 then
2
minus
-1 2
नेक्स्ट
-4
रो
0
ओके -4 0 कैसे आएगा सेकेंड वाली रो में? अच्छा नेक्स्ट लास्ट बताया आपने, ठीक है ठीक है ठीक है. So the properties of the matrix addition, we know they are commutative. A plus B is equal to B plus A. They are also associative, and you can say when we add 0 to a matrix, it is again the same matrix, and when we subtract the same matrix from itself, we get a 0 matrix. Then we move to the scalar multiplication. We have already done the scalar multiplication of the vectors. Now we take up the similar process we follow when we do the scalar multiplication of the matrices. So we multiply each element of the matrix with the scalar value. So here we say, like when we have a matrix of 2 by 2, that is 100, 200, 300, 400, and we multiply this vector A by a scalar value 5. So we are going to simply multiply each element of this matrix with the 5, and that will be the final answer that we get after multiplication of all the elements of this vector with 5. So similarly over here you can say scalar multiplication, when we have we multiply the any of the scalar values and we get the addition. So and similarly you do the multiplication. So all these values, you can say these are the various properties that follow for the scalar multiplication. 1 into A is equal to 0 and 1 into A is equal to 1. Then we move on to the, so that was a scalar multiplication. Here you can say it is a vector multiplication, or you can say the matrix multiplication, because when we say it is a vector multiplication, so that means we have 1D you can say the size of the matrix is equal to 1D. So here we can say that is called as array. So here when we talk about matrix, that means we have the size of the matrix is greater than 1, that is 2, 3, 4, any dimensions it may have. So both m and n, they have values greater than 1. So when we do this multiplication, we all know how we are doing it. So what we do, we multiply the row of first vector, first matrix with the column of second matrix. for the first element C11, first row with the second column of the second matrix, then we get C12. So similarly, we get C11, C12, C21, and C22, all the elements. So the new matrix that we are getting is 4 by 4. So similarly, here you can see the dot product of these two matrices that is shown in the example 1, 6, 9, 3. So we multiply 1, 6 with 0, 1, we get 6 minus 1, 0 minus 6, so we get minus 6. And then we have 1, 6 multiplied by minus 1 into 2, so minus 1 minus 12 plus 12, so that we get, right? And then we multiply 9, 3 with the 0 minus 1 and then minus 1, 2, so we get the second row. Similarly, we have the properties that are followed, you can say. So you can remember that these properties, and you may be knowing before that also. So 0 into A is equal to 0. That means if we multiply one matrix with a 0, so here 0 can be scalar or it can be a compatible matrix. I is basically the identity matrix. When we multiply identity matrix with A, we get the same matrix A. If then we say if we have two matrices A, B, and C, then B into C is equal to A into BC. So we can write as ABC. When we multiply AB with the two vectors we have, matrices, we multiply with the scalar alpha, then you have alpha into A into B. So these are the various properties which are satisfied, you can say, when we talk about the matrix multiplication. So these are the multiplication properties. Then we have matrix vector product. So we studied about vector multiplication. We studied about matrix multiplication. Now what we have is a matrix vector multiplication. So you can follow that when we multiply two matrices, the row of the first matrix is multiplied by the column of the second matrix, and then we take the addition. So you can say we have just one column, and then we will get, that means if it has one column, that means in the new matrix we will be getting only the two rows. So because the matrix has two rows, so plus 2 into 2 plus 3 into 3, so we get 13. Similarly, we multiply this and we get these values 13 and 13, because we have just one column. So the values of the other column we get only when we have the another column in the second matrix. So this is basically the matrix vector product. Any doubts if you have in between, you can ask. Just give me 1 minute. So when now we are computing another performing another operation, that is the inverse of a matrix. So the inverse of a square matrix A, if it exists, it is basically the unique matrix A inverse. So the inverse of a matrix it will be unique. So if matrix A has inverse, then it is called as inverter or non-singular matrix. If it does not have an inverse, then it is called as the singular or non-invertible matrix. So the general formula for computing the inverse of a 2 by 2 is, so how do we compute the inverse of a 2 by 2 matrix? Like here we have, so the inverse of a 2 matrix is AD, that means we are multiplying A with the D and we multiply then minus BC. So if it is equal to 0, then the matrix is singular, otherwise it is non-singular. Now you take out your pen and paper and you start working on this exercise. So I want to see the solutions that you have generated. So what we have is students, classes, and majors. We have three objects over here. You can say three entities. So we consider M students, N classes, and P majors. Each student can be in any number of classes between 3 to 6 and can be in any majors, that is 0, 1, or 2. So the data between the student classes and majors are given by a M by N matrix C. So we have to write the C matrix as an M by P matrix, where M, and then see what are the conditions. You can say Cij, the new value for this matrix is equal to 1 if student I is in class J, 0 if the student is not in class, and the second one case is Mij is equal to 1 if student I is in major and is equal to 0 if student is not in the major. Now consider let E be a n vector with Ai being the enrollment in class I. Express E using the matrix notation in terms of the matrices C and M. And the second one is define the n by me matrix S, where Sij is the total number of students in class I with major J. Express S using the matrix notation in terms of the matrices C and M. So understand this, what are we looking for, and try to find a solution.